Welcome. Welcome to the plasma physics course of TPFL. What is the trajectory of charged particles in given electric and magnetic fields? Well, in the past module, we have focused our attention on the simplest possible scenario, that is the one of a constant uniform magnetic field. We will now turn our attention to more complicated settings. We will first consider the one of a constant electric and magnetic field, and then we will turn our attention to the case of a non-uniform magnetic field. We have studied the trajectory of a charged particle in a static uniform magnetic field. Let's complicate a little bit the scenario. Let's add on top of this static uniform magnetic field a static uniform electric field. How a particle will move under the effect of these two forces? This is what we will see now, but let me already anticipate that the result will be quite surprising. So what we want to solve is a Newton equation of a particles with charge Q that is subject to an electric and magnetic field with the electric and magnetic field that are constant. To approach this problem, we will decompose this equation into direction parallel and perpendicular to the magnetic field. Let's start from the direction parallel to the magnetic field. Along the parallel direction, we will have that the mass times the acceleration is equal to the parallel electric force. And of course, the V cross B force will have no component in the parallel direction. What does it mean? Well, this is a very simple equation to be solved, which gives us a uniform accelerated motion. The perpendicular direction is of course more complicated. In this direction, what we will have to solve is mass times the acceleration in the perpendicular direction equal to the electric and magnetic force taken in the perpendicular direction. So what is the motion induced by these forces? Well, let's start to consider a simple case. Let's imagine that we have a magnetic field that comes out of this plane and an electric field that points upwards. So let's place a particle, a positively charged particle, Q greater than 0, and let's study the trajectory of this particle subject to these electric and magnetic fields. Okay, the particle is at rest. The first thing that it will do, well, it will be accelerated by the electric field upwards. Therefore, the particle will start to move upwards. At the same time, it will be subject to the magnetic field, and therefore its trajectory will be curved. And then the particle will start to move down. And while moving downwards, the electric field will slow it down. When the electric field slows it down, then the velocity decreases, and when the velocity decreases, the Larmor radius of the particle decreases. Therefore, the particles subject to the magnetic force will move and will turn this way, and then will be accelerated again in the direction of the electric field. Again, larger Larmor radius. Then the particle will move downwards. At the same time, will be slowed down, and the Larmor radius will become smaller, and then the particles will come up. This will be the trajectory. If you want, the guiding center of this particle will move in this direction, in a direction that is perpendicular to both the electric field and the magnetic field. Let's take the case of negatively charged particles that is initially at rest. Well, the particle will be accelerated by the electric field, this time downwards, because the particle is charged negatively. And then the particle will be subject to the magnetic field. It will gyrate with a a certain Larmor radius, and then particle, because of the gyration, will continue to move in this direction. But while moving in this direction, the particle will be slowed down, and therefore its Larmor radius will become smaller, and then the particle will continue to move, will be slowed down, etc. The result is that the particle's guiding center will still move in the same direction as the positively charged particle. So what do we expect from this image? Basically, that there will be a periodic motion on top of which a secular drift is present. So let's try first to understand what is this drift, and by averaging the trajectory over one gyro period. So we have to take this equation here for the perpendicular velocity and average over one gyro period. The averaging I will denote with these brackets, and therefore what we will have to evaluate is m dv perp over dt. That average over a gyro period will be equal to 0. And the gyro averaging the right hand side of this equation, we will have that this has to be equal to the gyro average of E perp plus the gyro average of V cross B. Now, as E perp and B are constant quantities, we can write this equality as the gyro average of V perp cross B equal to minus E. And now we can extract the value of V perp by crossing this expression with B. In fact, we will have that this, which using standard vector formula is equal to minus V perp gyro averaged B squared, and this has to be equal to E crossed with B, from which we can obtain immediately the gyro average value of V perp, a quantity that we will call with V, with the notation VE, and is equal to E perp cross B, this term here, divided by B squared. Now, this will be actually the velocity of the guiding center that, if you notice, as in the picture we have drawn, it's perpendicular to E and to B, and does not depend on the charge. Both positive and negative charges move in the same direction. Okay, so this is the averaged motion. How about the real motion? I mean, the full motion, the difference between the, if you want, the actual motion of the particles and the drift. We can decompose V perp as the sum of the VE velocity plus the perturbed quantity, if you want to call it this way, that will give this oscillation that we see here. We will write therefore that V perp will be equal to VE plus the difference between V perp and VE, that is a quantities that we will call V prime E, V prime perp. Okay, what is the equation that V prime perp is subject to? Well, we can rewrite the Newton equation that we have written here in terms of V and V prime perp, and this will be equal to m, the derivative of the perpendicular velocity that we have expressed in terms of these two quantities with respect to time. And VE is a constant quantity, therefore this will be equal to m derivative of V perp prime over dt, and this will be given by the forces that we have written here. where we have to decompose v perp as VE plus V prime perp. And this is equal to Q VE perp plus. Okay, we can explicitly write the value of VE. And then let's rewrite Q V perp prime cross B. Well, if you notice, this quantity is actually given by minus Q E perp. And therefore we'll cancel out with this Q E perp, and what we will obtain is simply Q V prime perp cross B. So now look at the equation that we have obtained by comparing this term here and this term here. Well, this is exactly the equation that we had seen before that gives a circular unit motion. So what are the conclusions of our exercise? Well, that the motion of a particle, of a charged particle in a static and uniform electric field is given by the superposition of gyro motion and drift motion of the guiding center. The drift motion is the VE term that we have introduced here, and it's an important quantity in plasma physics that is called the E cross B drift. The second observation that we want to do in this still relatively simple case is that the E cross B drift is independent of charge. Here in this expression there is no charge that appears. This is why the guiding center both for the positive and negative particle are moving in the same direction. By extending the observation that we have just done to the case of non-uniform electric field, we can observe that the particle is expected to move in the direction perpendicular to E, and therefore along the isocontour lines of the electrostatic potential. In other terms, the gyrocenter motion is along the isocontour lines of the electrostatic potential. Let's in fact imagine to have a magnetic field pointing out of the page. And let's imagine to have an electrostatic potential on the plane perpendicular to B with some isocontour lines. Now, as the E cross B velocity is in the direction perpendicular to E, and that E is perpendicular to the isocontour lines of the electrostatic potential, we will have that the particle, the charged particle, will move around following the isocontour lines of the electrostatic potential. The drift that we have just seen can be easily generalized to whatever force, uniform constant force that act on the charged particle. Basically, if we have to solve the Newton equation with a constant force on top of the Lorentz force, the V cross B force, well, if we solve this equation exactly following what we have done earlier with the electric field, we will find that the particle moves with the gyrocenter moving with the drift that is given by, that we will call Vf, and is given by the perpendicular component of the force perpendicular to the magnetic field cross B divided by Q B square. So let's see a couple of applications of drifts, of this drift that we have introduced here. The first one is the case of the gravitational force. Let's suppose to have a magnetic field pointing out of the plane, and then a gravitational force in this direction. will the plasma fall? So more precisely, let's suppose that we have a plasma here, and we are curious to know if subject to the gravitational force, the plasma will fall. Well, this is not actually the case, because the particles will fall adrift, will move according to a drift that for the ions goes in making the cross product between G and B, goes in this direction. So this will be the drift of the ions. So the electrons will move in this direction. Let's not forget that there is a charge dependence on the expression of the drift associated to the gravitational force. This is different than what we have for the electric force. And therefore the electrons will move in this direction. So just because of the presence of the gravitational force, the plasma will not fall. However, if we are careful, what will happen because of the presence of these two drifts? Well, we will have that a sort of positive charge will accumulate on this side of the plasma, while negative charges will accumulate on this side of the plasma. And what will be the result of the accumulation of these charges will be an electric field that points in this direction. And well, we have here an electric field, a magnetic field. What is the result? What is the result of this? It's an E cross B drift that is in this direction. And the E cross B drift is independent of the charge of the particles. Therefore, at the end, the plasma will fall down, but through a much more complicated process that one could think of by looking just at the resulting effect of the gravitational force. The second application that I would like to discuss with you is the curvature drift. Let's imagine to have a magnetic field lines with some curvature. And we will call this curvature the curvature vector with RB. Now, a particle will tend to move along the magnetic field lines, and as the motion in the direction perpendicular across B is sort of resisted. Therefore, while moving along the field line, the particle will feel a centrifugal force. That is the classic expression that we know. And therefore now, in the presence of a force and a magnetic field, we will have a drift that we can evaluate using the expression, and will be given by, we will call it Vd, curvature drift, which is the centrifugal force cross B, and using the expression for the centrifugal force, this will be given by the following expression. This, as I was saying, is what in plasma physics is called the curvature drift. And it's an important quantity, also this one, in plasma physics. Let's now consider the case of a non-uniform magnetic field, the one in which there is a gradient of the magnetic field perpendicular to the magnetic field itself. The scenario is therefore the following one. We have a magnetic field that points out of the plane, and which is subject to a gradient in this direction, perpendicular to B therefore. So let's suppose that we have a charged particles. Let's suppose that this has a charge, is positively charged. Now this particle may move, and because of the V cross B force, will tend to gyrate. And while it starts to gyrate, will experience regions where the magnetic field may become stronger, and when the magnetic field may become stronger, the Larmor radius will become smaller. And then when the particles goes back, we'll experience regions where the magnetic field is weaker and therefore the Larmor radius is larger. And then again regions where the magnetic field is stronger and therefore the Larmor radius smaller, etc. What is the result of such a motion? Is again the one that can be described by the motion of the guiding center of the particles in this direction. Now, what is the velocity of the drift of this guiding center? Well, the calculation is fairly complicated and you can find it in an appendix to the present lecture. Here I will just give the result, that is what you actually will need in the future. That is the V due to the gradient of the magnetic field is equal to the mass of the particle divided by 2b cube, V of the particles divided by the charge times the magnetic field cross the gradient of the magnetic field. As a matter of fact, as we see here, the guiding center will drift on a direction that is perpendicular to both grad B and B. This is what is called the grad B drift. In the present module, we have focused our attention on the trajectory of a particle in a given electric and magnetic field. In the past lecture, we had focused our attention on a quite simple case, the one of a uniform and a constant magnetic field. Here we have considered slightly more complicated cases. First of all, we have looked at what happens when there is a constant and uniform electric magnetic field, and then we have looked at what is the particle trajectory when the magnetic field is non-uniform. We have pointed out that in all cases the particle trajectory can be described as the superposition of a guiding center drift motion plus a gyro motion. And we have given the expression of this drift motion in all the relevant cases that we have analyzed.